The ability to perceive and understand 3D scenes is crucial for many applications in computer vision and robotics. Moving beyond common discriminative approaches, we introduce 3D neural embedding likelihood, or 3D NEL, as a generative, probabilistic inverse graphics take on the important problem of 6D pose estimation. 3D NEL defines the likelihood of real, noisy RGBD images given a 3D scene description through a principled combination of RGB and depth information. 6D pose estimation can be formulated as posterior inference using 3D NEL in an inverse graphics framework, for which we develop an efficient multi-stage inverse graphics pipeline. 3D NEL defines the probability of an observed RGBD image conditioned on a 3D scene description using an energy-based formulation. The 3D scene description consists of the number of known objects in the scene and their corresponding 6D poses. The 3D scene description is rendered into a depth image, which is transformed to a rendered point cloud image, a semantic segmentation map, and the object coordinate image, where each pixel contains the object frame coordinate of the surface point from which the pixel originates. The object coordinate image is transformed via a set of object-specific embedding models into key embeddings. The observed RGB image is transformed via another set of object-specific embedding models into query embeddings. The observed depth is transformed into an observed point cloud image. The 3D NEL energy function is evaluated using the rendered point cloud image, semantic segmentation, key embeddings, the observed point cloud image, and the query embeddings. Our proposed 3D NEL multi-stage inverse graphics pipeline starts by computing the query embeddings for each object and the observed point cloud image from RGBD observations. Then, a fast, coarse enumerative procedure produces a set of pose hypotheses for each object and constructs an initial 3D scene description. The initial 3D scene description is then refined using stochastic search with pose hypothesis proposals, ICP proposals, and random walk proposals. The result is a 3D scene description that explains the observed RGBD image. We evaluate on the YCB video dataset from the benchmark for 6D object pose estimation in the sim to real setup. Our proposed 3D NEL MSIGP significantly outperforms the previous state-of-the-art SURF EMB. However, the true distinction of 3D NEL lies in the array of probabilistic benefits it offers. Compared with existing, more discriminative approaches, 3D NEL's probabilistic formulation significantly reduces large error pose estimations and improves robustness. It is especially helpful in challenging situations, as shown in the above examples. Due to its probabilistic formulation, 3D NEL can also naturally quantify the pose uncertainties that may arise from partial observability, viewpoint ambiguity, and inherent symmetries of the object. 3D NEL's probabilistic formulation allows us to formulate object pose tracking from video as probabilistic inference in a state space model. Given a sequence of RGBD frames from a video, we use particle filtering to infer the posterior distribution and take the map estimate as our tracking estimate. Here we visualize tracking with 3D NEL on a representative video, where the tomato can gets fully occluded before reappearing. 3D NEL's joint modeling of multiple objects in a scene naturally handles occlusion through rendering and can reliably track through occlusion. We can additionally leverage 3D NEL's ability to quantify uncertainty to track an object through extended occlusion. Here we visualize tracking with 3D NEL in a challenging video with an extended occlusion. 3D NEL's probabilistic formulation provides a principled framework for incorporating prior knowledge about the scene and enables easy extension to camera pose tracking from video using inference in the same model without task-specific retraining. Given the assumption that an input video is observing a static scene, we can encode that assumption in our model by constraining all object poses to be transformed by the same amount between frames. Then the same inference procedure can be applied. The table demonstrates how incorporating the additional prior knowledge leads to comprehensive improvements over single frame predictions. Please refer to the paper and the open source code for more details. Thanks for listening.